Hi everybody, I am Pascal, professor at Télécom Paris, a grande école in France, Paris-Saclay. And the subject of this demonstration is demonstrating virtual I/O for Internet of Things device secured by TLS server in secure element. This demonstration presents an Internet of Things device, a thermostat, whose security is enforced by a secure element, that to say a smart card, running TLS server and using virtual input-output technology. The boards comprise a Wi-Fi system on chip, SoC, a microcontroller managing sensors, that's to say temperature probes, and actuators, that's to say relay, and a javacard. All device messages are sent received over TLS and processed by the secure element. Some of them are exported to microcontroller in clear form, which returns a response sent over TLS by the smart card. In previous work, we introduced the concept of four-quarter IoT secure architectures based on secure elements. Objects are built over a system on chip, SoC, providing communication resources, a general purpose unit, GPU, a secure element, that to say a smart card, running a TLS server, and a set of sensors and actuators. This demonstration illustrates the concept of virtual input-output pins for secure elements. The IoT device comprises a SoC, that to say a Wi-Fi chip, a secure element processor, that's to say a secure element microcontroller SEP, a secure element, that's to say smart cards, running a TLS server, a sensor, that's to say thermometer, and an actuator, that's to say a relay. Secure element has no I/O pin. The virtual I/O idea is to export in clear form, request, receive over TLS session to SEP chip, which returns a response in clear form to secure element. The thermostat boards comprise the following components: a low-cost Wi-Fi SoC ESP8266 Windows Day 1 Mini that costs about $2, with 80 MHz clock, 80 kilobyte SRAM, and 4 MB flash. A microcontroller ATmega 328, an Arduino Mini Pro, with 8 MHz clock, 2 kilobyte RAM, 32 kilobyte flash, which, as mentioned before, work as SEP. It communicates with the SoC through I2C bus, two interface WAR, SDA and SDL, using a 400 kHz clock frequency. It communicates with the smart cards with the ISO 7816 FireWire interface, comprising RAM, VCC, reset, CLK, and I/O. The smart card's clock is 2 MHz and is delivered thanks to pulse width modulation, PWM facility, what leads to a 186 microsecond bit time for ISO 7816 T=0 protocol. A GCOP javacard 3.05 with 3 kilobytes RAM and 85 kilobytes flash. A relay, that's to say actuators, whose pins are connected to SEP, a digital temperature sensor controlled by SEP. Now we are going to describe the software components. The SoC runs the TCP/IP daemons and manages only one session at a given time. It forwards TLS packet over I2C bus to and from SEP. I2C messages are encoded according to the following format: NAD 1 byte, PCB 1 byte, length 1 byte, optional payload, CRC 2 bytes. For outgoing master-to-slave TLS packets, payloads comprise ISO 7816 header 5 bytes concatenated to TLS packet. For ingoing slave-to-master TLS packets, payloads comprise TLS packet concatenated to ISO 7816 status 2 bytes. Thanks to this status byte, the SoC firmware knows the TLS session status, in progress, open, and close. When TLS secure channel is open, the secure elements may process commands for internal use, for example, PSK value modification. A command is a set of ASCII characters ended by carriage return and line feed character. They are received in encrypted form through the TLS PSK secure channel. A command beginning by an escape prefix, sharp, is decrypted and returned to SEP in clear form. The SEP executes the command. It returns a response to the secure element, which is thereafter transmitted within the TLS secure channel. A TLS packet has a 5-byte headers in clear form, which comprise 3 fields, type 1 byte, version 2 byte, and length 2 bytes. Virtual I/O messages are tagged by a null type. A SEP processes virtual I/O messages encoding at type equal to 0, version is equal to 0, length, I/O request, and TLS type 1 byte. The TLS response is an ASCII line ended by the TLS packet type, typically 17 in hexa for record lawyer. The SEP processes commands received over the I2C bus. It runs a library dedicated to ISO 7816 communication. It pushes TLS packet to the secure element and returns the TLS packet. The smart cards run a TLS SE, TLS for secure element application, written in javacard, a subset of the Java language. TLS SE is a TLS 1.3 server performing Diffie-Hellman exchanges over the SECP 256K1 elliptic curve. We use OpenSSL client to communicate with the thermostat with the following parameter: the server name and port, the TLS server name, key1.com, the elliptic curve group, the cipher suite, and the pressure key value. Now we are going to start the demonstration. The thermostat is connected on the Wi-Fi, and the remote client use OpenSSL. We have two serial line debug, one at SOC level, which show data exchange over I2C bus, and the other at the SEP level, which shows data exchange over ISO 7816 interface. There are three windows: SOC serial lines debug on left, SEP serial lines debug on right, and OpenSSL client on bottom left. We start a session with the thermostat. The thermostat is connected. An echo command is processed by TLS-SE smart cards. The sharp temp TLS IO command is received by smart cards and exported to SEP. The SEP returns the temperatures to smart cards that send it over TLS. We close the session with the thermostat. Thank you for your attention.